Welcome back everyone. In this lecture we will see the definition of inner semi-direct product, and from that I will motivate how to define external semi-direct product. Okay, so we will not actually get into too many details, but later we will use the concept of semi-direct product, and then I will tell you some applications of Sylow's theorem uh, with this. So let us start with the definition of inner semi-direct product, because which is something very easy to understand. So in the last class we saw a situation that G can be product of two subgroups. One is normal but another one is not normal, but still the intersection being trivial. Okay. So in that situation, we are actually only seeing that the only condition that differs from the direct product is that one of the subgroup is not being normal. Okay. So, but with this condition, let us see what one can actually get. So for that, let's prove a theorem. So let G be a group. Okay, again you can assume to be finite group. So with, let's say, H subgroup and N normal subgroup. Okay, so this is the condition is given. So then one can prove the following are equivalent. So what they are? So you can say that G is the product of these two groups and H intersection N is trivial. So this is something we saw naturally happening in one of the examples. So when order of the group is product of two distinct primes. So this is equivalent to G being again product Hn and H intersection N is trivial. So these two are equivalent is something very easy to verify. The third condition, which is somewhat very relevant, so this is relevant to actually I would say direct product. So G has this property for all element G in G. So this can be written uniquely, okay, as a product of elements from N and H. So there is a tuple NH from N cross H such that this G can be written as N times H. Okay, so now we can also change the role. Again, for all G in G, there exists again tuple NH, unique tuple, that is what important. G is equal to H. And the following is actually somewhat more important characterization of this semi-direct product. So which is called actually the group G is given by extension of H by N. Okay, so this is called the group G is given by an extension, not necessarily one extension, and extension of H by capital N. So what is the meaning of that? There is a natural group homomorphism. There is a natural group homomorphism from G to H such that when you restrict pi to H, that is the identity map on H, and when you take the kernel of pi, that is exactly N. So that means we have this split exact sequence, identity N G H identity. So this is actually a split exact sequence. Okay, so the condition that we have written here, there exists group homomorphism from G to H such that pi restriction H is identity and kernel pi is N, is same as saying that using this language of exact sequences, we have the split exact sequences. The splitting is actually happening here. So the splitting is given by the inclusion of H in G. Okay. So then in that case you say that the group G is given by an extension of H by N. And note that there are many possible extensions are there. Okay, and then so for the inner semi-direct product you already fixing H and N, and once you fix H and N inside G, the way H acts on N is also fixed, I will come in a minute like how H acts on N, we will see that. But before that, let us actually prove that these are all equivalent. But so 1 and 2 are equivalent is actually easy to see. So 1 if and only if 2, I will leave it as exercise, and similarly 3 if and only if 4 is also exercise. So all we do is 1 implies 3 and 3 implies 1, and 5 I will leave it as again exercise. Okay, so 1 if and only if 5, that also I will leave it as exercise. So what we are going to prove? We are going to prove that 1 implies 3 and 3 implies 1. So let us look at 1 implies 3. Okay. So what it says, given any element G that can be written as product of elements from capital N and capital H in a unique way. So we have to use that G is product of this N and H intersection N is identity. So let us prove this. Proof of 1 implies 3. So since G is NH for given G in G, you can see that G can be written as NH for some N in N and H in H. So that is trivial just from the definition of G equal to NH. So now in case G equal to NH and then N dash H dash, so then from this you can see that N dash inverse N is same as H dash H inverse. But these elements, so one element is in capital N, another element is in H. So this element should be in the intersection H intersection N, but which is trivial. That is what one says. So that means this N dash inverse N must be identity and H dash H inverse should be identity. That forces that N equal to N dash and H equal to H dash. So that means the tuple N and H is uniquely determined by the given element G. So this is what proves 1 implies 3. So now let us look at 3 implies 1 proof. So assume that any given element G can be written as product of elements from N cross H. So that immediately implies G must be equal to NH, because for any given G you have a tuple NH such as G equal to NH. That means if you take the product N and H, that should be exactly G. Note that N being normal in G, NH will be equal to Hn, so it must be a subgroup. So now using this condition in 3, you can see that G must be equal to NH. So now we want to prove that N intersection H must be trivial. So why that is the case? Let us start with X in N intersection H. Then this X can be written as now X times identity and identity times X. Note that X is coming from N and H. So that means the tuple XE is coming from N cross H, and as well as EX is also coming from N cross H. So there are two tuples now from N cross H such that X is written as product of those two elements XE and EX. But you know that there exists only one tuple such that this can happen. That means these two tuples must be equal. That forces that X equal to identity. So that means 3 implies 1. Okay. So it's somewhat easy characterizations. It is not that hard, but it actually possesses one of the important information that we usually have it for the direct group. That is, given any element G in G, there exists unique tuple N and H such that G equal to NH. Okay. So this is true for the direct products, but this is actually a characterization for semi-direct product. So now if you think about it, semi-direct products naturally arise in the context of group theory. So basically, so this extension of H by N, that is the natural thing. So the usually what we don't know, so we are interested in constructing G from the smaller groups groups. Okay. So this this N and H, both of them are smaller groups. So what you want to do, you want to actually somehow to find some group here in this middle, so that this becomes actually split exact sequence. If you construct something like that, then you can see that that group will satisfy these properties, that H and N become subgroup of that, such that H is subgroup and N is normal, and G will be NH and H intersection N is trivial. All these conditions will be satisfied. Okay, like I said, there are many non-isomorphic groups that can be filled in the middle. Okay, but in some situation, when you take that Z modulo PZ and Z modulo QZ, then there is only one way to fill in between. So that means there is only one non-isomorphic. Of course, one abelian group will be there, and one non-abelian group will be there. Okay, only those are the two things that you can fill here. So if you think about it, if you assume H is also normal, then this is actually like trivial exact sequence. So that means you can fill G to be H cross N. So basically, we are trying to generalize the concept of direct product. Okay, so if you take G equal to H cross N, so then both H and N are normal in G. Okay, so then whatever you are filling here in the position of G, that is the trivial thing that you are putting, that is the direct product. But somewhat we want to get a non-trivial groups coming out of from this N and H. Okay, so that's what we want to do. But unless we understand how one can actually do from the how one can construct from the smaller groups, then it is not complete. Okay, so but how one can actually start with the smaller groups and then construct such semi-direct products. So let us see from this inner semi-direct product itself. So basically, once we understand the inner semi-direct product, then we will be able to understand how to construct this external semi-direct product. So what I mean by that, so let us see, like once you are in this situation that G is semi-direct product of this H and N, then what other properties of this G can be recovered. Let us see. So first of all, there is a natural action of H on N. Okay, you take H and then you have this natural map phi from H to automorphism of N, that is given by, let us say, H goes to P phi H. So how the phi H is defined, which is a map from N to N. So you just normalize given element, X goes to Hx H inverse. Okay, so I will leave it to you to check this is indeed group homomorphism. Okay, so check G is phi is a group homomorphism. So this is easy. So now using this group homomorphism, what we want to do, we want to write down the product of elements of G. Okay, so we know that given any element of this G can be written as product of elements from N and H. Okay, let us use that. So let us take G dash from G. Then you know that G can be written as some NH. G can be written as NH and G dash is written as N dash H dash. So in the direct product, what happens if you take G dash in the direct product? So this is going to be NH N dash H dash, but these two things will actually commute. So this is H, this is H dash. So this will be exactly N dash H dash. So this is what will happen in the direct product, but that is not going to happen in the semi-direct product because one is normal, another one is not normal. So then closely look at what happens to G dash. So this is going to be exactly N H N dash H dash. So now what I can do, I can multiply by H dash inverse and H dash. So you take N H. Okay, so maybe I will do it here. So I want to bring N dash here. N dash, I group them, and then N dash inverse. Sorry, I need to do it the other way. So because this H is acting on here. So let's write G equal to Hn and H dash N dash. Okay, so both are possible. So then if you take this is Hn H dash N dash. So this is going to be H dash and then H dash N H dash inverse H dash N dash. Okay, this is how I am grouping. So then, so all I am using G equal to Hn. So that's all I am saying. So then you can see that G dash is equal to H dash. So this is happening in H. Okay, this is just a product in H. So now here you can see that this is H dash inverse N H dash and then N dash. So this is another product. But if you think about it, this is exactly H dash and then this is what? This is phi H dash inverse applied on N and then you are taking N dash. So indeed what is happening here, okay, so this is just a product that is happening in H which is G dash, but this is also element in capital N, okay, but instead of taking N dash, this is the usual product. So this is the usual product in capital N, but what we are doing, we are taking this twisted product which we call it N star N dash given by this phi. So what is this? This is you apply phi H dash inverse on N and then you multiply by N dash. Okay. So basically given tuple H N and then H dash N dash. Okay. So you want to define the product. The product actually comes uses this phi. Okay. So you can simply take, okay, for example, to construct G, all we are going to say that G is just a Cartesian product of H and N because there exists unique tuple H n such that G equal to H n for all G in G. So that means as a set it is exactly can be identified with H cross n as a set, no issue. But on this set we are defining a new product using this automorphism phi. Okay. So that tells you that if you take this Hn H dash N dash, both Hn and H dash N dash, they come from this H cross N. Okay, this is the set, a new product. So this is the new product which uses this phi and then you are defining it to be H dash comma. Now look at phi H dash inverse, apply it on N and then multiply with N dash. So this is your new product. Okay. So this twist is happening in the second component. So this is the twisted product, it is not the usual product. If it is the usual product, then what you get is direct product. But now you are making a twist. This is the twisted product using this automorphism phi, So that is why you are getting something funny, and this product of course depending upon phi. So such a group, okay, one can verify that this is indeed a group and this is actually given by this automorphism phi. Okay, this is semi-direct product of H and N or extension of H by N using this automorphism phi. Okay, so this is either called extension of H by N using this automorphism phi or the semi-direct product of H by N. Okay, so this is the way you construct new group using two given groups and this extra information that phi, which is a map from H to automorphism of N. Okay, now there are many things needs to be checked. Okay, I will leave it to you to check that this H cross N with respect to this new product is indeed a group, Okay. So what I mean by that, okay, so basically what is the data I am starting with? I am starting with a two group H and N. So these are all two groups and then you have another automorphism from H to automorphism of N. which is denoted by h goes to phi h, and then phi h is a map from n to n, and this is just a home automorphism. Okay, this is just automorphism, not necessarily given by the conjugation. Okay, so then using this data, we are taking this set h cross n and defining this star phi, okay, on these elements on h cross n. How we are defining? You take two element h n and then define this h dash n dash. So this is going to be h dash and then phi h dash inverse applied on n and then multiply with n dash. Okay. So now we are claiming that this h cross n with respect to this star phi, it is actually a group which is called semi-direct product of h by n using this automorphism phi, okay, or the extension of h by n using this automorphism phi. And of course, by definition you can see that these semi-direct products are, they very much depend upon this automorphism that you choose. Okay. So maybe you take it as exercise. If you take z modulo pz and then semi-direct product with z modulo qz when p divides q minus 1, then you get so this doesn't depend upon the choice of automorphism, from h to automorphism. Okay, in the non-abelian case, Okay, so that means you will be getting up to isomorphism only one semi-direct product. Okay, so this actually kind of gives you some information about semi-direct product. As I said, okay, I am just outlining the concept of semi-direct product, which naturally motivated from the inner semi-direct product. So now you can check that the usual properties of groups satisfied using the information given. Okay, so now let us see some more applications of actually Seiler's theorem. Okay, so I will actually end with one important application, so one can make it as a theorem. So if order of G is less than 60 and G is simple, so then one can claim that order of G must be a prime which is less than 60. Okay, what is a simple group? Recall that G is simple if it doesn't have any proper non-trivial normal subgroup. Okay, so if you take a group of order which is less than 60 and if it is simple, then you can prove that the only such group is prime order groups. So that means if you take a group of order which is less than 60 and if it has prime factorization, at least two primes are involved. Okay, so then you can see that that must be actually not simple. Okay, that's what this is. So we have already looked at these examples. When order of G is prime square, it is abelian. So this case we are done. Order of G is PQ and P and Q are distinct primes, we have done because we showed that Silo Q subgroup must be always normal. So this case is also done. So then what will be the remaining order? So if you just go through the all numbers from 1 to 60, so then the remaining orders will be like something like this: 12, 18, 20, 24, etc. Okay, and then you can choose each and every number and then check it. It cannot be simple. So I will actually demonstrate just for two particular orders. So let us start with order being, let's say, 12. So I will do only one or two examples. Okay, so then you can see that this 12 is actually 2 square into 3. So now we claim that this must be not simple. That means it must have a normal subgroup. Okay, so let us use these Seiler's theorems and then conclude what happens. So let us look at N3. it is number of silo 3 subgroups. So then the n3 should divide 2 square and then n3 should be congruent to 1 modulo 3. Now the chances are n3 is 1, 2, 2 square. Now since n3 is congruent to 1 modulo 3, so 2 cannot appear. So 2 cannot appear, but it can be 4, either 1 or 4. But if it is not normal, okay, because we want to claim that there is one normal, okay, assume that there is no normal, then that forces that n3 is 4. Now similarly look at n2. So n2 divides 3, so n2 must be either 1 or 3, but n2 is, let's say, congruent to 1 modulo 2. So then you can see that n2 can be either 1 or 3, both are possible. But if n2 is not equal to 1, then that forces that n2 is 3. If n2 is 1, then we are done, okay, otherwise n2 will be 3. So let us see that n2 3 and n3 4 both cannot happen, okay. If both cannot happen, then one of them must be 1. That is what our analysis says. So why both cannot happen? So if you take for example n2 is 3, so that means there are 3 silo 2 subgroups. Silo 2 subgroups must have order 4, okay. So that means if you remove this trivial element, then if you look at one particular silo 2 subgroup which has order 4, except the identity, all other elements will have order 2 or 4, okay. So that means the number of elements of order 2 or 2 square is going to be, there are 3 groups, so 3 into remove the identity, so 3 into 3, that is 9. Okay. So similarly the number of elements of order, so if you take silo 3 subgroup that has order 3, identity, except identity, all other elements will have order 3. So if you take number of elements of order 3, that is going to be, there are 4 groups, remove identity, so then it will be just 4 into 2, which is 8. So then if you add identity 1 plus 9 plus 8, then the order of the group should be at least this. But what is this? This is actually 10 plus 8, 18, which is a contradiction, because our group is given to be having order 12. So we started with group which has order 12. So that forces that, so both cannot be 3 and 4. That means one of them should be 1. That means group of order 12 must have normal subgroup of either, so either silo 2 subgroup is normal or silo 3 subgroup is normal. That is what it says. Okay. Similarly, let us look at another group, let us say the group of order 30, and then you can divide this into 2 into 3 into 5. Now look at n5. So n5 divides 2 into 3, and then n5 is congruent to 1 modulo 5. So this forces n5 either 1 or 6, because it cannot be 2, 2 is not congruent to 1 modulo 5, and it cannot be 3, 3 is not congruent to 1 modulo 5. So that means n5 is either 1 or 6. Now n5 is 1, then we are done. So assume that n5 is 6. Okay, otherwise we are done. So now let us look at n3. So n3 divides 2 into 5. So then you can see that n3 is congruent to 1 modulo 3. So that forces that n3 is either 1 or 2 or 5 or 10, but 2 and 5 both are not congruent to 1 modulo 3. So this is just either 1 or 10, because 2 is not congruent to 1 and then 5 is not congruent to 1 modulo 3. Okay. So that means n3 has to be either 1 or 10. If n3 is 1, then we are done. So assume that n3 is 10. Okay. So once you assume n5 is 6 and n3 is 10, that is already huge. So you have assumed N5 is 6 and N3 is 10. So now let's look at silo 5 subgroup. There are 6 subgroups that you are saying, but if you take any non-identity element, that will be having order 5. So the number of elements of order 5 is exactly 6 into 4, that is already 24. Now if you take number of elements of order 3, so then you can see that because silo 3 subgroup has order 3, silo 5 subgroup has order 5. So this is again you take non-identity element in each subgroup, that will have order 3. So that means 10 into 2, which is 20. But this is already 44. But 44 is strictly greater than 30, which is a contradiction, because we are started with a group of order 30. We can't have 44 elements in that group. So this counting says that one of this N5 or N3 is 1. There is no other option. That means one of them must be normal subgroup. So similar analysis can be done for all other possible orders, okay, which is strictly less than 60. We already seen that A5, which has order 60, is actually a simple group, and one can prove that that is actually smallest simple group, okay, but this is the analysis that we are doing, okay. So maybe like I will end with one or two actually exercises, okay. Again, these are all applications of Seiler's theorem. For example, if you take the order of the group to be p square q, so then you can see that G is not simple. Even including p equal to q case one can handle, because when p equal to q, it is a group of order p cube, which is p group, then center must be non-trivial, that we have already seen. When p is not equal to q, again we will have G is not simple, okay. That is something you can verify directly. Suppose you have a group of order 2p and G is not abelian. So then one can prove that this G must be isomorphic to the dihedral group D2p, okay. Again, this can be done in two different ways, either use Cauchy's theorem, or you can just directly use Seiler's theorem and then prove the existence of order 2 and order p subgroups, and then order p subgroup must be normal, okay. So you take this p to be odd prime. So this is odd prime. So then you can prove that this subgroup of order p must be normal, and it must be unique. So G must be actually semi-direct product of this Z modulo 2Z and Z modulo PZ, which is you can prove it to be isomorphic to the dihedral group of order 2p. Okay, so that is how the proof goes. Okay, so one can actually make much more applications. Mostly like Seiler's theorems can be used in understanding groups of small orders. Of course, once you are comfortable with the semi-direct product, then you can easily see that the groups of small orders can be actually constructed from other groups of really small orders, okay. And then if you want to actually try to see whether some given group is simple or not, again using this analysis of if you are dealing with really group of small orders like p square q, the number of prime factors are very less, then immediately you can conclude that, okay, something about the simplicity of the group using Seiler's theorem, okay. So these are all some important applications of Seiler's theorem. Okay, with this we are actually ending with the applications of Seiler's theorem. Okay, I will stop here. So we will continue in the next class with the structure theorem of finite abelian groups. Okay, thank you very much.